Now let's talk about entropy transfer with heat flow. Okay. Now first of all, let's recall that ds is equal to dq for a reversible process upon T. So when heat is added to a system, dq is positive, okay, and when heat is removed from a system, dq is negative, okay. So for a positive dq, the entropy increases, and for a negative dq, the entropy decreases, okay. Now if you take a system of a fixed mass, let us say this is a system, okay, where the mass is constant, nothing is going in, nothing is going out, so it can be a closed system, okay. So when you transfer heat to the system of a fixed mass, so when you transfer heat into the system, okay, it increases the internal energy of this system, and as a result of which the molecules of this system, let us say it has a gas inside, okay. So when we add heat into this system of a constant mass, let us say it has a gas, so upon adding heat into it, the molecules move with higher kinetic energy. So the kinetic energy increases upon addition of heat, and the frequency of collision also increases. So they collide more frequently. It also increases, okay, and this means the disorder in the system increases. So heat is thus regarded as a disorganized or disordered energy transfer, which increases the molecular chaos. Now this is very important, okay. So if you look at this, this is basically, so heat, okay. Now when heat was positive, so in this case when you add heat to a system, it is positive and the entropy increases, okay, and when you remove heat from a system, the entropy decreases and the heat is negative, okay. So in this case we are adding heat, and the addition of heat is bringing about an increase in the kinetic energy and in the frequency of collision. This means the chaos inside the gas molecules increases. Now we also know that the increase, that is the addition of heat, also brings about an increase in the entropy. Now we are saying upon increasing or upon adding heat, the you can say the molecular chaos or the disorganization within the molecules is increasing. This means increased chaos indicates increased entropy. So entropy is basically, you can say a measure of the disorientation or the disorganization or the molecular chaos within the system, okay. So this is what it indicates physically, if you want to understand that, okay. Now let's look at this figure, and in this figure let us say that heat Q, and this is the heat Q, it flows reversibly from the system to the surroundings, and this happens at temperature T0, okay. Now when this happens, that is the heat flows reversibly from system to surroundings, the entropy increase of the surrounding, because we are adding heat to the surroundings, so the entropy of the surroundings would increase, okay. So I can say that delta S surroundings would be equal to plus Q upon T0, okay. And similarly the entropy of the system will reduce because heat is going out of the system, okay. So you can say that delta S system, this is equal to minus Q upon T0. So this is very easy to understand now, okay. Now if you go back to the figure and look at that, and look at the figure, now the temperature of the boundary, now this is the boundary, the temperature of the boundary where the heat transfer is occurring, because heat and work, they are both boundary phenomena, okay. So the heat transfer which is occurring at the boundary, and the boundary is at constant temperature T0. So let us say this much is the boundary across which the heat is flowing, and this boundary is also at temperature T naught. It can be said that the system has lost entropy to the surroundings. Okay, system has lost entropy to the surroundings. So we can say that, or we can say that the surroundings have gained entropy from the system. Okay, so the system has lost entropy to the surroundings, or you can say surroundings have gained entropy from the system. Okay, so this is what it is. So this means that there is entropy transfer from the system to the surrounding along the heat flow, because heat flows from high temperature to low temperature. So let us assume that system is at a high temperature and surroundings is at a low temperature. So as the heat is flowing from system to surrounding, there is also entropy transfer from system to the surroundings. Okay, so in other words, we can say that since the heat inflow increases, because in surroundings we are throwing heat, so the heat inflow to the surroundings is increasing, the molecular disorder or the molecular chaos, I just wrote it down somewhere, yes, the molecular chaos, it is also increasing. Okay, so therefore the entropy increases for surroundings, and as the heat is flowing out of the system, the chaotic nature of molecules will reduce, so the entropy will also reduce. Okay, so we can now actually stretch a correlation between entropy increase and the heat flow, or entropy decrease and heat flow. Now, on the other hand, there is no entropy transfer associated with work. So this is very important. There is some entropy transfer associated with the heat flow, but no entropy transfer associated with work. So let's look at a diagram to understand this. So let me draw a diagram for this. Okay, so this is a simple looking flywheel. Okay, very simplistic schematic of it, and this is the control volume. Okay, now we have a system over here. It can be any system. Let's not go into the nitty-gritties of it. Just consider the system. It is giving some work input to the flywheel. So let us say this is the flywheel. Okay, now what is happening is, in this figure, if you look at this figure, the system, it delivers some work to the flywheel. So there is a work transfer from system to the flywheel. Now in this flywheel, there is some energy which is stored, and this energy which is stored in the flywheel is in fully recoverable form. Okay, so flywheel stores energy in fully recoverable form. So you can actually 100% recover energy which is stored in the flywheel. Now the flywheel molecules are simply put into rotation, because it rotates as well, isn't it? So they're simply put into rotation around the axis in a perfectly organized manner. So there is no dissipation, and hence no entropy increase of the flywheel. The same can be said about the work transfer in the compensation of a spring or in raising of a weight by a certain height. So if you have a spring system, okay, so if you have a spring system, now there is no entropy transfer along with work. Now if work is dissipated adiabatically into the internal energy increase of the system, which we talked about when we had a system with a adiabatic viscous fluid into it, you can say a insulated viscous fluid which had a stirring mechanism, and we were putting some work into this system. So in this case the work is dissipated adiabatically. Okay, so if the work is dissipated adiabatically as the internal energy increase of the system, yes, we can say there is an entropy increase of the system, but there is no you can say that there is no, as such, no entropy transfer to it. Okay, so what is happening is, you input work into this system. Now due to this work get transferred into the increment of the internal energy of the system, but this basically increases the entropy of the system, but there is no entropy transfer, that is from surrounding to system or from system to surrounding. There is no such transfer taking place. Okay, so to summarize, I can say that entropy transfer is possible. Now this transfer can be from system to surrounding or from surrounding to system. Is possible in heat transfer, or when heat is flowing from one body to the other body. Okay, but no entropy transfer is possible in work transfer. So these two things are of high importance, because there is no disorientation or there is no chaos in the molecules of the flywheel in this case. Similarly, you can say it for a spring. Okay, and also the case when we saw the mechanical irreversibilities being explained, that is you put in the work, it increases the internal energy, which increases the entropy, but there is no transfer of entropy from somewhere else. Okay, so this finishes this video, which explains the concept of entropy transfer with heat flow and then compares it with the entropy transfer with the workflow. Now in the next video we will look at the entropy generation in a closed system.